So with that out of the way, I think we can go ahead and get started. So our first talk is going to be by Dr. Howard Bond. He is an astronomer at Penn State, and he is going to be telling us about weird light reflection and refraction in space.
Yeah, sure. Sure.
Okay, so just to introduce myself, my name is Bond, Howard Bond, and I'm a professor of practice at Penn State, which is a fancy title for a semi-retired adjunct professor. I also spent about 25 years with the NASA Hubble Space Telescope project, and I'm an astronomer emeritus with the Space Telescope Sciences. Now I'll be showing some spectacular images from the Hubble Space Telescope, which was launched in 1990. None of us involved in the project thought it would still be producing excellent science 28 years later, but there it is, orbiting the Earth every 96 minutes or so. Now, you may have learned in grade school that light rays in space always travel in a straight line. But if you believe that's always true, you are wrong. And I'll give two examples of light rays in space not traveling in a straight line. The first one will be light echoes, and the second will be bending of light rays by massive objects. Well, to introduce light echoes, I'll start with the well-known concept of sound echoes. And so we often experience sound waves echoing. A good example is if there's a lightning producing thunder, the sound of the thunder comes straight to you, but it also can bounce around off of nearby objects, and that sound arrives later because of the relatively slow speed of sound. So we call that a sound echo. Or maybe after Astronomy on Tap, you'll go out to the mountains and emit sounds, and you'll hear the sounds echoing off of the hills. So that's another example of echoes. Now, why don't we see echoes with light? Because the lightning flash, the light comes straight to us, but can also bounce off the clouds and nearby hills and so forth. Why don't we see light echoes? Because, exactly, the light does echo, but it happens so fast that we can't see it. Light travels 186,000 miles per second, or it works out to about 1 foot per nanosecond. So when we go to bodies in space, separated by very large distances, measured in light years, then we can see light echoing in space. Now, here's a cartoon showing what could happen. Here's a star that suddenly explodes, becomes bright, and it's surrounded by interstellar dust clouds. Let's play that again. So the light comes straight to us. We're down in this direction. The light comes straight to us. Also goes out to the side and then comes to us, but later on, because of the additional length that the light had to travel. So we call that a light echo. And to get a light echo, you have to have two things. First, you have to have a star that suddenly gets brighter, like it explodes or erupts or something. And there has to be dust around it up to the side to reflect the light, and that light comes to us later. So the combination of this happening is very rare in astronomy, but we had a brilliant case of it happening in the year 2002 with the star V838 Manasseh. And in the background of this slide, you can see the light echo. So, first of all, the name V838 means that it's the 838th variable star cataloged in the constellation Monoceros, or the Unicorn, which just lies to the left of Orion. Not a very famous constellation, but that's where this star exploded. An amateur astronomer discovered the explosion, and then later on, there was this spectacular light echo, which we observed several times with the Hubble Space Telescope. So the explosion was in January 2002. Here's our first Hubble image. Here's the star that exploded. It's already gotten fainter again. And then this glow around it is the echo of light from the explosion that went out to the side and then arrived at the Earth 5 months later. And then we continue to follow it. So now the light, later in 2002, the light has moved further out to the side, then comes to us. October and December 2002. So it's kind of like throwing a stone into a pond, and you see these ripples going out around the star that got brighter temporarily. Here's probably our most famous image of the light echo taken in 2004. I'll come back to this image later. But of course, we made an animation. So this is over 4 years, showing the light then propagating out into the dust and then coming to the Earth and forming the light echo. So we were, of course, it helps to have a telescope in space with the very sharp images that the Hubble Space Telescope can obtain. So what did we learn from this event? A bunch of things. First of all, we know the speed of light, so we can work out then from how the light echo appears to grow, how far away the star is. And the answer is 20,000 light years. So actually, this explosion occurred, you have to think of it this way, 20,000 years ago, but the light only reached us in 2002. And then you can also, since we know how far away it was, we can work out how bright the star was, and it turns out it was one of the brightest stars in the entire Milky Way for a month or two. And then many people have been looking into the cause of the explosions of this star. And it's generally believed now that it was actually a collision or a merger of a binary star. The two stars came together and then released a tremendous amount of energy due to this collision. And so if that picture is right, it's a new type of stellar explosion that we just discovered back in 2002. So just here are some computer simulations then that theoretical astrophysicists are working out, showing how a binary star can come together and eventually merge to make a single star. So again, as I say, this is a new type of event in astronomy. We kind of knew that stars could merge, but I think most of us didn't realize it could happen literally in a matter of weeks and not take thousands of years. So, now as I mentioned, the Hubble telescope was launched in 1990, and in 2015, for the 25th anniversary of Hubble, NASA organized a kind of a bracket arrangement where they took a whole bunch of the best images taken by Hubble, and then people would vote on the internet. And we whittled it down from 16 to 8 to 4, and finally to 2 of the top images of Hubble. So naturally, I was voting for this. And I think about 20,000 people voted, but unfortunately, there was an upset, and the Eagle Nebula got number 1. So we came in second, but nothing to be ashamed of. Okay, so I think that's the story of light echoes. Now let me turn to another way that light does not travel in a straight line. It's the bending of light rays by massive objects in space. And this goes back to Albert Einstein, his general theory of relativity, which was published a century ago now. And according to general relativity, space-time is warped near a massive object, for example, like our sun. So here's Einstein, and this kind of illustrates the concept of warped space. You can think of a trampoline with a bowling ball sitting on it. And then if you were to shoot marbles past the bowling ball, the path of the marble would be curved. So the same thing happens in three-dimensional space, for example, around the sun. And so Einstein had predicted that if you're here on the Earth looking at a star and the sun is in the way, of course, normally the sun would blot out the nearby star because the sun is so bright. But if you did this during an eclipse of the sun, you would see that a star that's really there would appear to be deflected away from the sun because of the curved path of the light. So Einstein had made this prediction. Then at the solar eclipse of 1919, astronomers actually went out, photographed the eclipse. You could barely see it. A couple of stars are marked here. And the astronomers knew where those stars were located in the sky when the sun isn't there, and compared where they were when the sun was there. And sure enough, they were displaced away from the sun. So this was one of the great scientific results of the 20th century. I went and dug up the New York Times from 1919. And here's the announcement of this discovery. And there's this great quotation here. It says that Einstein's prediction was one of the greatest, perhaps the greatest of achievements in the history of human thought. And it was this that actually made Einstein a celebrity. And after this, Einstein, at least up to the time of Stephen Hawking, was probably the most famous scientist in the world. It was primarily because of this prediction that he had made and then was verified. So, now, coming up to the present time, we decided, a colleague of mine led our team to reproduce this measurement, but using another star outside the solar system. In fact, it's a white dwarf star. It's a very compact star that's reached the end of its life. And this white dwarf slowly moves across the sky, and it passed almost exactly in front of a background star. So you expect to see the same thing. Here's where the star really is, but when the white dwarf is just in front of it, that star will appear to deflect its position. So we set out to measure that with the Hubble Space Telescope. Here's the concept in this cartoon. Here's the warp space. The white dwarf passes in front of the background star, and it will deflect its position. Now, this cartoon greatly exaggerates the amount of shift. Here's an actual image with the Hubble Space Telescope. Here's the white dwarf. There's the faint background star. And these are the positions at which we made the measurements with the Hubble Space Telescope. And now the white dwarf appears to wobble across the sky as it moves. You know why? It's the effect of the parallax. That is, as the Earth and the Hubble telescope go around the sun, our viewing angle changes slightly. So that's why the path appears to wobble. And here are the actual Hubble images of the white dwarf passing by that faint background star. And we measured the deflection. The amount of deflection was an angle of 2 milliarc seconds. That's 2 1,000ths of a second of arc. A second of arc is a 60th of a minute of arc. A minute of arc is a 60th of a degree. This is a really tiny angle. But with the Hubble telescope's sharp view, we could actually make the measurement of that deflection. And again. Well, I presented these results at a conference on white dwarfs in Santa Fe, New Mexico recently. And just for fun, I worked out, so if I'm standing in Santa Fe, and I have an object in State College, and I want that object to cover an angle of 2 milliarc seconds, which we measured with the Hubble Space Telescope, how big would that object be? You want to guess? Astronomy grad students want to guess? Small.
Dime.
Huh?
Dime.
A dime. Whoa! Did you cheat? It's actually a quarter, but you're very close. So a U.S. quarter sitting in State College and viewed from 1,500 miles away subtends an angle of 2 milliarcseconds. And we could measure that with the Hubble Space Telescope. I had to check this calculation several times, but it's true. So, what did we learn? So the amount of deflection tells you the mass of the white dwarf. So in most cases in astronomy, to measure the mass of a star, you have to have a binary star. This is a single star. We measured its mass by how much it deflected the background star. And the answer is that its mass is 67.5% the mass of our sun. We also were able to work out its radius, and it's just slightly larger, or its diameter. This white dwarf is just slightly larger than the Earth. So knowing the mass and the diameter, you can calculate, for example, its density. And the average density of the white dwarf is 640,000 grams per cc. Or, if you like English units, it's 11.6 tons per cubic inch. I took a cubic inch of that white dwarf and set it on this table and crashed to the floor. So that's the final state of stars like the sun. When they use up all their fuel, they'll end up as a white dwarf, more or less like this one. And by the way, all these numbers agree very well with the theoretical astrophysics work and the structure of white dwarfs. So this actually, we made the cover of Science magazine with this story. Not this medical thing here, but up here in the corner. Just a couple weeks ago, Discover magazine ran a story on the top 100 science stories of 2017, and we were number 49 with this repeat of the famous Einstein experiment of 100 years ago. So, light rays in space do not always travel in a straight line, and we can learn new things about the universe when they don't. Thank you. Oh,
Could I ask you a question about Hubble?
yes?
Is
See.
that reaction wheels?
Yes, Hubble has. The question was, how do we move Hubble? There's no fuel on the Hubble telescope. It's all done with reaction wheels, like big weights.
It's amazing it lasted that long.
And if you change the, sorry, what?
It's amazing it lasted that long when you consider Swift as a human reaction.
Well, I think all of us with the project are astounded. We're still getting great data 28 years later.
And when
We did lose some gyros. The astronauts have been up to Hubble several times and replaced the gyros, so we're actually in pretty good shape right now.
one more question about Hubble.
Yeah.
When the web goes out and everything works out fine,
Right.
will they decommission and let Hubble?
Well, we're hoping there'll be several years of overlap with Hubble and the James Webb Telescope, both operating. They're somewhat different telescopes. So the James Webb is mostly infrared,
Right.
and it's a much bigger telescope than Hubble. And it'd be out actually beyond the moon. There's no way astronauts can work on the James Webb, so that's got to work the first time.
Will it be at a Lagrange point?
Yeah.
Oh, will.
Oh, sorry. The Webb will be at what's called the Lagrange point.
Yeah.
It's a point out the Sun, Earth, and then the James Webb will be out there. It's a semi-stable point for an orbit. Whereas the Hubble orbits the Earth every 96 minutes.
Thank you.
And we're hoping that the Webb will go up next year, but it's starting to look a little doubtful.
Any other questions?
On your echo,
Yeah.
your images kind of just remind me of like normal like dust or ejecta from a supernova or whatever, like expanding. But you're convinced that's actual just that's light at light speed.
Yeah. A lot of people have the impression, as you point out, that we're seeing material expanding away.
Yeah.
Which we do see in other cases, although never that fast. But in this case, we know that it's only the light moving. It's like It's like Indiana Jones, you know, in the temple of whatever in Egypt, lighting his torch, and he can see all these wonderful things, and the torch burns out. So you just had that one chance to see that dust illuminate, and then the light is gone. So the echo is gone now. It's over with. But that's just dust that was there all along, just minding its own business, and it got suddenly flashed by this exploding star.
Other questions?
Way back here. If the Hubble were reversed 180 degrees, would it be able to focus on the surface of the Earth? And if so, what would the resolution be?
First of all, so the question is, what if you turn Hubble around and look at the
Look
Earth?
back up.
And by the way, we actually do point Hubble at the Earth, but it's moving so fast that any image you take would be completely blurred. So it's not designed to image the Earth.
I know that. But could it be? But if you did,
Well, it's kind of based on the same technology that's used on the dark side.
yeah, that's what I'm
Or
getting.
telescopes that do image, but we're not equipped to image it. It's just completely blurred with the technology we use. Also, it'd be out of focus.
Yeah. Okay. So the
When you get there, even though it's 300 miles up, it'd be out of focus.
He wants to spy on his neighbor. Just wondering how good it looks.
I'm afraid you'll have to use. I'm sure there are other assets up there that can do what you do.
but not as big as the Hubble.
Oh yeah. Well, there's that. I mean, there actually was a telescope, more or less a duplicate of Hubble, that was built for the Defense Department. And we're actually planning now. The Defense Department decided they didn't need it. I think it was in a garage in Rochester or something. I don't know the exact story. But it's being modified to be a space telescope, which we're calling W first. The Wide Field Infrared Survey Telescope, I think that's what it stands for. And hopefully it'll be launched in the 2020s, although the latest budget was canceled. So hopefully our friends in Congress will get it back in the budget. So that'll be a kind of a reuse of a satellite originally built to image the Earth and changed for astronomy.
A reground lens, I assume.
Yeah, well, there's a sad story about the mirror of Hubble. Oh, yeah, I asked about the grinding the mirror. There was a flaw in the grinding of the mirror for Hubble. It's kind of a long, unpleasant story. But it was all by a fraction of human hair, which is enough to put the images out of focus. But the astronauts went up in 1993 to correct that. And since 1993, and you've seen the quality of the images we're getting. It's fantastic now.
Yes, thanks, Dr. Ball.